Hello, and welcome to a lecture on characterization of antenna patterns. My name is Steve Ellingson. Here's the outline of this lecture. First, I'll remind you about the fields of an electrically short electric current element, which I will abbreviate as ES-ECE for brevity. In this lecture, the purpose of using or talking about this particular thing is to demonstrate the concepts of antenna pattern characterization. So this isn't really about electric current elements, it's just useful to demonstrate the concepts using this particular thing. First, E and H plane patterns. I'll explain what those are, sometimes referred to as pattern cuts. Then I'll define and give you examples of normalized field and power patterns. We'll talk about directivity. Then I'll talk about characterization of the pattern. So this is where we talk about main lobe, half power beam width, and other pattern concepts. Radiation intensity, beam solid angle, and then gain and efficiency. Okay, first, a reminder about the fields of an electrically short electric current element. Here I've drawn it in the Cartesian coordinate system with the current element aligned along the z-axis. The length of the current element is L, and because it's electrically short, we're saying it's much, much less than a wavelength in length. And the current is directed upward with current I. So here is the electric field that results from that electric current element, and here's the magnetic field intensity that results from that current element. And these, of course, are the far field expressions. And then a little picture here to remind you what the magnitude of the fields look like. There's a null in the z direction and a maximum in the rho direction. Okay, first, pattern cuts. Here we talk about the E and the H plane. The E plane is the plane in which the electric field vector lies. For the electric current element, which is z-directed, the electric field vector is always theta polarized. I should say specifically theta hat polarized. So the E plane is any plane containing the z-axis, because any plane containing the z-axis also contains the theta hat vector. So here is a picture of the E-plane for the ECE that's oriented along the z-axis. There is this null along the z-axis, and then there's the maximum in any direction rho pointing perpendicular to the z-axis. The H-plane is the plane in which the magnetic field vector lies. Now for this current element, H is phi polarized. So the H-plane is the z equals 0 plane. So here's x, here's y. The magnitude of H is constant all along here, and in fact the H field vector goes like this in a circle. That's phi hat. Now again, I'm showing this for the ECE, which is z-directed, but this concept can be applied to any antenna, although it's not always unambiguous, but there usually is an E and an H plane that you can identify. Okay, radiation pattern characterization. So there's a bunch of quantities that we want to talk about in this lecture. Here I've just listed them to have them all down one place. Normalized field pattern, which is, I'll give the symbol capital F. Normalized power pattern, the directivity, and then the radiation intensity. And all these things are functions of theta and phi for a current distribution, or an antenna representable as a current distribution, which is clustered around the origin of the coordinate system. And then I'll talk about beam solid angle as well. In order to do this, I want to show you a generic way to talk about the pattern of a antenna or a current distribution which is clustered around the origin of a coordinate system. If we have that, and we're in the far field, then the electric field can always be written in this form. Here's your spherical wave. There is some function of theta and phi, which I've called E sub naught. which is a complex valued thing, and then a unit vector, which is simply the direction in which the electric field vector points. So, for the electric current element that we've been talking about, here is the far field electric field expression. In this case, it's obvious that theta hat is E hat, and that E sub naught is this expression, sine theta j omega mu, the current moment, I times L divided by 4 pi. So in these terms, the normalized field pattern can be defined as E sub naught divided by the value E sub naught in whatever direction maximizes that quantity. So what you do is you consider all the values of E sub naught over a sphere surrounding the antenna. You find the one that has the maximum magnitude, and then use this to normalize the actual value E sub naught. So, for example, for our electrically short electric current element, E sub naught is this, as I pointed out in the previous slide. And then we want to divide it by the maximum value of that quantity. The maximum value of that quantity is simply this, because the thing which maximizes that quantity is when theta equals pi over 2, because that gives you sine theta equals 1. You do that division, and you find that the normalized field pattern in this case is just sine theta. So the normalized field pattern of an electrically short electric current element is just sine theta. Note that it turns out to be real valued in this example, but in general it could be complex. In other words, the normalized field pattern could be complex valued, so we have a magnitude and a phase. However, the maximum magnitude will always be exactly equal to 1 by definition. Now the normalized power pattern. In terms of the field pattern, the normalized power pattern is simply the square of the magnitude of the field pattern. So, for example, you will note that this has voltage-like units, right? Not voltage units, but voltage-like units. And if we square that, then we get power-like units. Right? Again, this is actually unitless, but it's their normalized power. This is usually expressed in log units in most engineering applications. So we'll describe the power pattern in dB in the usual way, 10 log 10 of the power-like units, or 20 log 10 of voltage-like units. So you can either square before, or you can square after, whatever suits you. So why bother with the power pattern? It's a convenient way to describe patterns for 3 reasons. First, it's in terms of power, but independent of the choice of units. Right? So we're talking about something which is proportional to power, but we don't have to say whether it's watts or milliwatts or microwatts or watts per meter squared or something like that. It's simply proportional to power. Second reason is it's independent of range. By doing this normalization, we have removed the range dependence. We have a simple 1 over r range dependence in the magnitude, 1 over r squared in power, but we normalize that out. So this power pattern now is independent of range, and we no longer have to say how far away we are from the antenna. We simply have to know that we're in the far field. Third reason, has a maximum value of 1, 0 dB, so it's really easy to compare the patterns. So for the electrically short electric current element, the normalized magnitude pattern, the normalized field pattern was sine theta, so the normalized power pattern is magnitude sine theta squared. Now, directivity. Directivity is formally defined as the power density in some direction, theta phi, because directivity is a function of theta and phi, divided by the power density for an isotropic antenna. So the idea is you can apply a certain amount of power to a given antenna. You can measure how much power density, that's watts per meter squared, it puts out in the far field. And then you could repeat the experiment for a isotropic antenna, and it would put out so many watts per square meter in the far field. And you compare the two, and that tells you the directivity. So directivity tells you how much higher or how much greater power density is emitted in a certain direction compared to an isotropic antenna, which is an antenna which emits uniform power density in all directions. Now, there's another way to think about this, and it's a corollary to the definition. We could forget about the theta and phi dependence and simply say we're interested in the maximum directivity. In that case, the maximum directivity is the power density in the direction in which it is maximum divided by the power density averaged over all directions. And I'll say usually when antenna engineers talk about directivity, this is usually what they mean. They normally mean maximum directivity. So the directivity of the electrically short electric current element, well, let me show you how to get that. So here's the magnitude of the electric field squared. For the electrically short electric current element, it's this. We just square all the factors. And just note that the only thing here which varies with direction is that sine theta term. So we know that the magnitude of the electric field squared is proportional to sine squared theta. Now the maximum power density is in the direction theta equals pi over 2, right? Here's z, here's rho, here's theta, right? So when theta is pi over 2, that's when the pattern is maximized, right? The pattern looks like this. The average power density, let me erase some of this. The average power density is the total power radiated through a sphere of radius r divided by the area of a sphere. So if we have this sine squared theta as the power pattern, we integrate over a sphere which surrounds the antenna, and the area of a sphere is 4 pi r squared. So now if we work this through, we get sine squared theta here. ds is r squared sine theta d phi. That's straightforward calculus. We integrate over theta, we integrate over phi, and when the smoke clears, we end up with 2/3. So we can say for the electrically short electric current element, the directivity is 1, right? The value here, divided by 2/3, the value here. That gives you 3/2, which is 1.5. And if we write that in dB, that gives us 1.76 dB. And normally we add this little I here to the end. That's to indicate it's dB relative to an isotropic antenna. Now for directivity, that's a little bit redundant, but it can be useful to say dBi because there are other ways actually that you can say directivity. For example, you can say directivity relative to a dipole as opposed to an isotropic antenna. So I normally won't do that, but or at least I'll warn you if I do. Normally when I talk about directivity, it'll be formal directivity, and that has units of dBi. Okay, some features of the power pattern. So here's a highly directive antenna. Highly directive antennas typically have a main lobe. So here's a main lobe. If we show this in terms of the normalized power pattern, the peak of the main lobe will be 0 dB, and really I should say 0 dBi, isotropic. We can define a half power point where the power has decreased to a value, the normalized power pattern has decreased to a value of 0.5, or we say 3 dB down from the maximum. So that's the definition of the half power point. And in fact, the distance between half power points in the main lobe is referred to as the half power beam width. Here it's written HP. More commonly, it's written as HPBW, half power beam width. So that's the distance between the half power points in some plane. I'll point out the half power beam width can be different in the E plane and the H plane for the same antenna because the patterns can be different for the same antenna. Also, we have this characterization known as the beam width between first nulls. And the idea here is that the main lobe eventually disappears, goes into a null, and then comes back out into the first side lobe. So between those points, there is often a discernible null. and you can find that on both sides of the main lobe, and it defines the main lobe. And then this distance between the nulls is known as beam width between first nulls, or BWFN. And then, of course, if the antenna is very directional, we have minor lobes. So that's what's being drawn here. So antennas which are directional, and certainly antennas which are highly directional, like large phased arrays and large reflector antennas, we typically have a picture that looks very much like this. Here is a half-power beam width of the electrically short electric current element, just to provide an opportunity to come up with a number. Remember, the normalized power pattern for the electrically short electric current element is the magnitude of sine theta squared. Here it's drawn out. The point at which the normalized power pattern is reduced from 1, which is what it is here, to 1/2 occurs when theta is equal to pi over 4. So from this we can obtain the half-power beam width simply because, well, we've already figured out it's pi over 4 on one side. It's going to be, by symmetry, 3 pi over 4 on the other side. So we have pi over 2 as the total angle, or we can say 90 degrees. So this distance here to here is 90 degrees. That's half-power beam width. We can also draw these patterns in various scales. So in linear units, the power pattern is a maximum of 1 here. The half-power beam width is defined between the points at which the normalized power pattern has dropped to a value of 1/2. But if we show it in terms of a voltage pattern, we can show it this way. In terms of the voltage, the value is dropped only to the 1 over the square root of 2. And the half-power beam width hasn't changed. We're just simply showing it as magnitude or voltage pattern as opposed to a power pattern. In either case, the half-power beam width is the same, because half-power beam width is defined as angle between half-power points. And I'll say once again, note half-power beam width is often different in the E and the H planes. In fact, ask yourself, what is half-power beam width of an electrically short electric current element in the H plane? In the H plane, the pattern looks like this. There are no 3 dB points. So the electrically short electric current element, and more generally, omnidirectional antennas, do not have a half-power beam width in the plane in which they're omnidirectional. Okay, now the concept of radiation intensity. Recall that the total power radiated by an antenna, and that has units of watts, is given by an integral. This integral has inside the pointing vector that has units of watts per meter squared, or power density, dotted into this differential element here, which has units of meters squared. It's a differential surface element. So that gives us watts. So we can obtain the total power radiated by an antenna by picking some sphere which surrounds the antenna. Here's the antenna of the current element here. We pick some sphere S, which encloses the antenna. We measure the power density at each point. We integrate around that sphere, and we get the total power. If we write that out a little bit more formally, we can show this as an integral over a spherical surface, in which theta goes from 0 to pi, phi goes from 0 to 2 pi. We can replace the pointing vector here with a slightly expanded notation where we show explicitly how many watts per meter squared are flowing through a certain point, theta prime, phi prime, and the radial vector, which shows the direction of power flow. And then we can also expand ds prime in terms of the spherical coordinate system. So there's the radial unit vector, r squared, sine theta prime, d theta prime, d phi prime. Now, r hat prime and r hat prime dotted together obviously give you 1, so that goes away. So this expression simplifies pretty quickly. But note, now we have watts per square meter times meters squared. We have the power density times the distance to the field point squared. We give this quantity the symbol u. It's a function of theta and phi. and we call it the radiation intensity. And in fact, we say this has units of watts per steradian. Watts per steradian. Steradian is a unit of solid angle. Solid angle means if we have a sphere and we start at the origin, we can go out to the surface of the sphere and we can identify some chunk of the surface. Well, we refer to this two-dimensional angle as a solid angle, or as steradians. So steradians are the solid angle generalization of radians. This quantity, the radiation intensity, is independent of R because the power density is a function of reciprocal distance squared. In other words, the power density, being watts per meter squared, decreases as you get further and further away. Right? We have a high power density close to the origin, and as we get further out, the power density drops by at a rate of 1 over r squared. So this has a 1 over r squared in it. We multiply it by r squared. So the radiation intensity is independent of r, which is one of the reasons we like to talk about it. Radiation intensity, watts per steradian, independent of the distance. Now this whole thing, sine theta prime, d theta prime, d phi prime, we refer to as the differential solid angle. A solid angle having units of steradians, as I've just explained. So now we put this all back together. Same expression that we started off with, or same quantity that we want to evaluate, but now we can say it's an integral over a sphere of the radiation intensity, U, integrated over solid angle. So let me show you some examples. So for an isotropic antenna, and that's one that produces a uniform power density as a function of theta and phi, well, we see right away that the radiation intensity must be a constant with respect to theta and phi. So we can figure out what the total power is using the previous expression. That's radiation intensity integrated over solid angle. Solid angle is just a constant, so we get this expression. Since radiation intensity is a constant, we can pull out of the integral. So for an isotropic antenna, we find that the radiated power is 4 pi times the radiation intensity. That's the relationship for an isotropic antenna. Note that the average radiation intensity over an enclosing sphere for any antenna, so this could be true for any antenna, we can compute the average radiation intensity. That's just the radiation intensity divided by the number of steradians in a sphere, which is 4 pi. So the numerator is just the total power. The denominator is just the number of steradians in a sphere. So the average radiation intensity for any antenna is power divided by 4 pi, the number of steradians in a sphere. Another way to write this exact same relationship is to say the total power radiated by an antenna is 4 pi times the average radiation intensity. So if we know the average radiation intensity for some antenna, then we immediately know how much power it's radiating. This brings us to the idea of beam solid angle. Recall that directivity is maximum power density divided by the average power density. That is the power density averaged over a sphere enclosing the antenna. So we can multiply the top and the bottom of this expression by r squared, as I've done here. I've just multiplied by r squared over r squared. And power density times r squared is radiation intensity. So I find that directivity can be calculated as the maximum radiation intensity divided by the average radiation intensity. Now let me make a definition. I will define the beam solid angle, this quantity omega sub A, as being the total power divided by the maximum radiation intensity. If I do that, I can replace the numerator here with the defining expression for beam solid angle. That's P divided by omega sub A. We see that the P's cancel out, and I end up with 4 pi over omega sub A. So apparently this definition here, this beam solid angle, is closely related to the concept of directivity. So let me reiterate, we have this quantity, omega sub A, we call it the beam solid angle, has units of steradians, and simply an alternative way of expressing directivity. Now, let me show you one way that we can exploit this. It turns out that you can quickly compute the beam solid angle as an integral over a sphere of the normalized power pattern. So if I know the normalized power pattern, I can simply integrate over solid angle, a sphere surrounding that source, and I immediately get the beam solid angle. And then from the beam solid angle, I can get the directivity. So this often provides a quicker way of computing the directivity, or a more convenient way of computing the directivity. Here's an example. Sometimes in phased array work, we like to come up with simple models for the pattern. Here's an example. So we have some generic phased array here, and we come up with the simplest possible pattern. Now I should point out, this pattern is utterly non-physical. No phased array, no antenna has a pattern like what I'm about to show. But for some kinds of work, it's useful to have a very simple model. Even though it's non-physical, it might be good enough for the purpose. In this model, the antenna is directive. It's directive in the z-hat direction. And it has a constant magnitude normalized power pattern from theta equals 0 to theta equals theta naught. So over this range, we say the pattern is constant. And outside that range, we say it's 0. So this pattern is either full strength or it's 0. We can compute the directivity of this pattern very quickly using the relationship I showed previously. We just integrate over the normalized power pattern. You can do this integral. It's quite simple because this quantity is either 1 or 0. So it's a good exercise just to make sure you know how to do the relevant integration. But the result is that the beam solid angle is equal to 2 pi times the quantity 1 minus cosine theta naught, where theta naught is this opening angle in the pattern. Then we can compute the directivity. Directivity is just 4 pi over beam solid angle, so we get 2 divided by quantity 1 minus cosine theta. Now you can check your work here, and I suggest you do this. First, ask yourself, does this result give you the expected result for an isotropic antenna? In terms of this model, an isotropic antenna is one which has theta naught equal to pi. In other words, the opening angle is pi. So you could ask yourself, does this expression give you the right angle give you the right directivity for a isotropic antenna? The second thing you can ask yourself is, does this give you the expected result when the beam width goes to 0? So in other words, if theta naught goes to 0, what happens? And is that the expected behavior? So I won't go through those two checks with you, but you should, and make sure they make sense to you. Okay, now let's talk about gain. Formally, the difference between directivity and gain is efficiency. Efficiency is all the things that you can do to reduce the implied power density to some smaller number. So remember, directivity is a way of talking about power density, but power density relative to that of an isotropic antenna. So if I say the power density, the directivity has been reduced by some number, I'm really saying that the power density that I expect has been reduced by some amount. And we refer to the new relative power density as gain. So obviously the range of values that this efficiency could take on goes from 0 to 1. 1 would mean that gain is equal to directivity. 0 would mean that no matter how much power I apply to this antenna, nothing ends up in the far field. So what are some reasons why epsilon, or the efficiency, might be less than 1? Well, one common reason, especially for small antennas, is when ohmic losses of materials exist in the materials from which the antenna is constructed. So, for example, if you have a patch antenna, the patch antenna is built on some substrate, which is usually a dielectric, and that dielectric has some loss in it. And that loss absorbs some of the power that would otherwise be radiated, and so the gain is different from the directivity. The power density in the far field is less than what we expect because some of the power got absorbed by the dielectric. Another way we can have gain less than directivity is when there is absorption of power into surroundings by electromagnetic coupling. So for example, this is a big problem for HF antennas in the HF band, say between 3 and 30 megahertz. What happens is, at these frequencies, wavelengths are huge. They're on the order of tens of meters. If that's the case, then any antenna is coupled into the ground over which it is mounted. And so some fraction of the power applied to the antenna ends up being dissipated into the ground through electromagnetic coupling between the antenna and the ground. So that's a form of efficiency loss. Another efficiency loss mechanism applies to reflector antennas. So think about a reflector antenna here. That's a parabolic dish. There's a horn. That horn radiates and illuminates the antenna. And nominally, that reflector culminates the radiation from the feed so that all the power ends up going in the same direction. That's the way reflectors are supposed to work. Of course, what happens is that there is no way to design a feed system which illuminates only the reflector and doesn't, in part, illuminate things around the reflector through an overshoot mechanism, through over-illumination. And if that's the case, then the power which spills over, which misses the reflector, represents an efficiency loss because that's power which is not being collimated, not being sent in the proper direction. So for reflector antennas, we have significant efficiency losses because it's hard to match feeds to reflectors without having some spillover. Now, there are other ways we can have reduced efficiency, but I'm just trying to give you an example of a few that are common. This concludes this lecture on characterization of antenna patterns.